Today, I am here to present Poised, spotting Twitter spam off the beaten path. And this is a collaboration work with Francois Labege and Alireza Sadeghian, Alizan, Jose Fernandez, Christopher Kurgel, Gianluca Stringani, and Giovanni Vinia from UC Santa Barbara, École Polytechnique de Montreal, and University College London. So every day,
Excuse me. Could you hold the mic?
oh, sorry.
Thank you.
Every day we hear some news about how social networks are abused by cyber criminals to spread spam and malicious content. News about fake accounts, spam bots, and scam and phishing attacks, and recently fake news. And they use this for several reasons. First of all, social networks provide a large victim base because they have hundreds of millions of users. Also, they benefit from the inherent trust between connected users to spread malicious data more effectively. And previous related work, tried to detect spam messages by detecting malicious messages using how, for example, they have some malicious URLs in them, or detecting malicious accounts, trying to detect compromised accounts and civil communities. And unlike other previous work that only focused on detecting spam based on content and accounts, we propose Poised, which spots spam messages by their diffusion patterns throughout the network. And in our attack model, we don't have any constraint on the type of spam messages and the accounts posting them. And we assume that the spam messages are posted in larger scale and they're similar in content and format. But they can be sent by any of fake accounts, compromised accounts, and social bots. Spam detection is an adversarial problem. In a real setting, adversary tries to um, understand how detection works and actively attempt to evade it. And in our attack model, we actually assume the attacker has all these capabilities, but we assume that the adversary is only able to compromise some partitions and not the whole social networks. And Poised was inspired by Homophily Principle, where individuals tend to associate and bond with similar others. And there are vast array of work that show that in social networks, people try to connect to people who have the same characteristics as themselves. And based on this, we came up with this hypothesis that if in a social network people are connected to each other based on homophily principle, then they should share similar topics of interest, especially among network communities. And we manually checked a small Twitter network. And interestingly, we found 3 different communities of interest, each having very specific set of topics of interest. But even some not neighbor communities can be interested in the same topics. For example, at the time, some messages about some soccer match can be sent in both red and blue communities. And again, in time 2 and time n, similar messages appear in these 2 communities about some other soccer matches. And so based on this, we can say these communities are interested in same topic, but they are not neighbors, they are far away. And we call these sets of communities interested in the same set of topics parties of interest. But a community can be part of several parties of interest. For example, at time k, again, it has in red and green communities, same messages are appearing, but there, for example, are about computer security. So these 2 communities are talking about different topics. They're interested in computer security. So if we know a message is appearing in red community, we can build a probabilistic model on if this message can be seen in any other community. Based on this, we came to hypothesis 2, and we hypothesized that malicious users have different patterns in terms of propagation throughout the network. For example, at some time, messages being set in red, yellow, and dark blue communities. This is not normal, and we don't expect that these messages appear in these communities. And probably it's a malicious content. Based on this hypothesis, we construct Poised, and Poised builds a probabilistic model based on diffusion of messages throughout parties of interest, and then uses machine learning to detect spam messages. The first step is data collection. The second is trying to detect communities and the topics that are speak in communities. And then we cluster similar messages, build a probabilistic model based on message propagation, and then train the classifier and trying to find spam messages. And as you can see, in each step, there are several steps. And there are some details on the methods we are using and the parameters we are using that I'm not going to talk about in the sake of time. But you can read the paper. And in December 2015, we crawled using Twitter API. We tried to collect data. We crawled timelines for 300 random users. We call them seeds. And we also crawled the timelines for their friends and followers. And we call the seeds with their friends and followers a neighborhood. So in total, we have data for 300 neighborhoods. And in total, the data set includes about 82,000 users and 15 million tweets. Then for each neighborhood, we constructed 2 networks, directed and undirected, and using following relationship between users inside the neighborhood. And for detecting communities, structural communities, we use a very well-known community detection algorithm called InfoMap. And using that, we detected a total of 2,300 communities. Then we want to find topics of interest of these communities. For that, we divided timelines of users in each community into documents, and we use LDA to detect topics of interest of communities. And then the collection of all these topics would be topics for that community. And then we examine our hypothesis 1 by using entropy-based metrics, including completeness and homogeneity. Completeness measures if all documents of a community are about the same topic, and homogeneity measures if a topic is only talked about in a single community. Higher completeness means that members of a community are interested in the same topics. For example, they're all talking about soccer only. And higher homogeneity means that communities have distinguishable topics of interest. So each community is talking about different topics. And to compare, to have a baseline and compare if actually in social networks we are having communities of interest, we constructed a null model, which is a random network that the documents are partitioned randomly in it. And for example, we have this network. This is a real network. It only has 2 communities and with 500 documents with some topics. Then we create this random network that has exactly the same number of communities, the same number of documents, but the documents are shuffled and randomly put in any of these communities. So this would be our null model. And we compute the homogeneity and completeness measures and compare those results with the real network. And here, this plot shows the comparison of these values. And we see that both homogeneity and completeness, when we have random networks, null model, drop substantially. And this proves that actually in social networks, we have communities of interest. After having communities of interest, we want to find clusters of similar messages and construct the probabilistic model based on how they are propagated in the network. For that, we use four-gram analysis, which groups um, messages that share 4 or more consecutive words into clusters. For example, in these social networks, these white messages are appear in different parts of the network. And for example, they're about soccer. So we call all these messages a group of similar messages. And we pick top 5,000 groups of similar messages, ordering by their size. And then we manually label them. We hired a group of 14 security researchers, and we asked them to categorize each group into spam, app, quote, and normal. And by app, I mean some applications are posting messages on behalf of users on social networks. For example, uh, health-related messages are posted by fitness trackers. And this table shows some of the messages that are labeled by our researchers. Then having this ground truth, we want to know how they are propagated in different communities. For example, we have these communities and we already know they are talking about this set of topics. And then we have one group of similar messages that appear in red and blue communities. Then in our probabilistic table, we have a row for this group of similar messages. And the columns are all the union of topics that we have identified in the network. And each entry shows the number of times that messages are appearing in communities with interest in these topics. For example, here, for this group of similar messages, group 1, both community 1 and community 2 have interest in topic 1. So we sum these messages and put the number in the first entry for topic 1. For topic 2, community 1 only has interest in topic 2. So the value for it would be 20. And we normalize it by dividing to the total number of messages in that group. And then, again, in another example, here we have group 2, which the messages are appearing in community 1 and community 3. And since both communities are interested in topic 1, again, the topic 1 has the sum of all the messages. And since only community 3 has interest in topic 4 and 5, then the topic 4 and 5 would be 5 and in the probabilistic table. After building this probabilistic table, we use machine learning to detect a spam and detect each group of messages as a spam or benign. And into the features, we also added number of users divided by number of messages, because some of these messages are only posted by one user. Some of them are sent by many users, and that can be an indicator. And our class is defined as a binary variable. It can be benign or spam, but if you remember, when we manually labeled the groups, we had 4 categories: spam, normal, and quote, and app. So we came up with 3 different combinations that make more sense. And in combination 1, we include the spam in a spam and other categories in benign. In combination 2, we have a spam in a spam and normal in benign. And in combination 3, we have a spam and app in a spam and normal and quote in benign. The data set is unbalanced, and we have more benign messages than fake messages. So we use a very well-known technique, which is oversampling technique to work with unbalanced data. It is called a SMOTE. And we tested multiple classification algorithm, naive-Bayes, SVM, random forest. And to evaluate, we ran K cross-validations with different values of K. And no matter what classification algorithm we are using, or the number of K, or what combination of classes we are using, it shows a great performance. Sorry. For example, we have 91% precision and 93% recall for combination tree. And after finding these groups of messages being spam or benign, we use Poised to detect spam accounts by examining the distribution of users' messages. So this plot shows the histogram for percentage of users' spam messages. As you can see, there are two categories. Many users only send benign messages. There are normal users. Some users are only sending spam messages. There are spammers. But there are some people in between. These can be compromised accounts, or they can be users trying to be acting as normal to not detected by Twitter. And it's hard to tell, but by looking at the data, we decided to pick a threshold of 40%. If more than 40% of tweets for a user are spam, so we call this user a spammer. And creating this data set of normal users and spammers, then we tested uh, three different state-of-the-art systems, including a spam detector, which detects fake accounts, examining user profile characteristics, and Compa, which is the system trying to detect compromised accounts by flagging abnormal user behaviors, and Butternut system that detects social bots using thousands of features, trying to see if they're similar to known characteristics of bots. And as you can see, all these systems are performing poor. They cannot detect spam accounts. And the reason is that these systems can only detect certain types of spam. They're trying to detect only fake accounts or compromised accounts or bots, while Poise aims to detect any malicious message. And then we investigated how Poise is doing when we don't have the full knowledge of all the messages and all the network. We simulated this. We assume that we only have data about some percentage of communities, and then see if we can detect spam. And this graph shows the performance based on percentage of affected communities. You can see when we know more about communities, the detection is better. But even when we have knowledge about 30% of communities, still Poise effectively detects spam messages with 90% precision and 70% recall. And spam detection is an adversarial problem. And we try to investigate how robust is Poised when in adversarial settings. And we assume that some communities are compromised. An attacker, for example, has some civil accounts in it or can post in those communities. And also can observe how benign messages are posted in those compromised communities. And then try to make the propagation of her spam messages as similar as possible to the benign messages in those compromised communities. For example, here we have three communities, and we have one group of similar messages, and then two communities are compromised, community 3 and 2. The adversary learns about this group and tries to send the exact amount of spams in those communities whenever the messages are appearing. So in our probabilistic model, we will have a new row for this group of similar messages. And you can see that here for topic 4 and topic 5, the amounts, the values are the same as group 1. However, since community 1 is not compromised, the values for other topics don't match. So based on this, we think that still Poised can detect spam messages. And but as you can see, this is adding noise to the data. And this noise can be added at the training phase or at the testing phase. And these are called poisoning attacks and evasion attacks. And we evaluated Poised for both of them. At the case of poisoning attack, at the training phase, the adversary attempts to mislead the classifier by poisoning training data. So he learns, and then at the training set, we have this noisy data. But at the evasion attack, at the testing phase, the adversary carefully manipulates attack samples to evade detection. So the simulation would be the same, but but for the training set, we don't have this noise in our data set. We are using with unpoisoned original data, but on the testing set, we have this noise. And this plot shows the performance when the x-axis is showing the percentage of compromised accounts. We can see that when more communities are compromised, our performance or Poised performance decreases gradually. And it shows that the adversary needs to have a lot of knowledge about the network and compromise the whole network to be very effective. For example, if 30% of network is compromised, the precision and recon remain at 82% and 87% in the case of poisoning attack, and at the 75 and 52% in the case of an evasion attack. In summary, Poised is the first system that detects spam messages by predicting the diffusion patterns of messages in the social network. It outperforms other state-of-the-art detection systems, and our simulation results show that spam messages can be detected early on, and Poised is difficult to evade for an active adversary. With that, I finish my talk. Thank you for listening, and I will be very happy to answer your questions.
So hi, so nice work, Yang Zhang from Cispa University. So I was wondering, so you use the information, I mean, this diffusion pattern to detect a spam message. So I will consider to combine other kind of information to make this your detector stronger. And for example, I don't know, social network structure, you can use it to also do that. And if you combine all things together, the result will be better or somehow similar or even they reduce it.
That's a really great question. We didn't evaluate this, but I suspect that usually when you want to find a spam detection, you should have a tool of devices. And I think using other techniques, adding more features would be beneficial. Yeah, this can be a future work.